Hello YouTube viewers, welcome to my channel S2T, and in today's show Science to Thursday we're going to talk about fuels. We have already looked into jet engines, their types and their subsystems. So today we're going to look deeper into the thing that basically makes it run. So we are talking about liquid energy. Now you need lot of power for flight, and if you paid any attention to description, like technical description of plane, they will always specify it like powered flight. Now why does that quote unquote powered flight matter? Because you can make a plane from your paper and you throw it and it will fly using your basically energy from your hand. Now again, that's not powered flight because it's not self-sustaining. That is why we always specify powered flight. Is it a powered flight or is it a glider? Because there are many things that are just glide, or there are many things that you drop from another plane and it will just glide. So to differentiate, we always add the word power to it. Now to do anything in space industry or rocket industry, like be it Raptor engines or things of that nature, or J12 or something like that, you always need lot of power. Now fuel is energy, so what the hell is power? Now this is one thing that is super easy to understand. Think of it this way: energy is joules. Basically it's how many unit of something you have, then you add one another unit to it, basically time, how many units you are consuming per unit of time, you get power. That's the whole reality of it. Energy basically it's okay, 100 watt. What does that mean? That means nothing. Basically 100 watt over a course of, let's say, 1 hour. Okay, that's 100 watt an hour, but let's say 100 watt in a second, that's a lot of power. You consumed a hell lot of power there. So that's the reality of it. So, and that is another reason why rocket engines require liquid oxygen, because fuel, basically RP1 or JP1, they are quote unquote same. Basically they are not too dissimilar from each other. Both are made out of kerosene. So why can't a rocket engine just utilize atmospheric oxygen? Because oxygen in atmosphere is barely 20%, 22% if you're really generous with it, and you get 80% nitrogen. That nitrogen is going through your combustion chamber, reducing its oomph. So in case of rocket, you need this puppy to cross a gravity well, so it needs a lot of oomph. So how do you get that? You remove the nitrogen. So what do? You give it liquid oxygen. So that's the reality of it. It's not the energy itself matters, it's how quickly you can extract it. Like the power aspect matters a whole lot, and that is why we don't always use one thing for everything. Basically that is why you don't have, oh, gasoline is used for basically for your scooty, and same thing is used for a locomotive, same thing is used for a giant freight ship or things of that nature. There is always a different demand because the power requirement is different in each of them. So power on this planet always comes from more or less hydrocarbon. Now hydrocarbon generally, the way we are using, but the industrial kind, it generally comes from crude oil. Basically crude oil gives us every tom dick and everything that you can see. Every form of energy, one way or the another, generally comes from that, unless you are talking about like solar or wind or renewables basically. So crude oil is the base of it. Now why is crude oil so powerful? Because it inherent term, like if you take crude oil, you simplify it, you remove impurity and all that jazz, all you are left with carbon and hydrogen. Now because Earth's atmosphere is very unique and it has free oxygen. Now that is a very critical aspect, because you can say, hey, water also has oxygen, but that oxygen is bounded. It is bounded to hydrogen. Basically it's stable state, it's not reactive anymore. When you're talking about oxygen in atmosphere, it's O2, it's self-bonded, it's basically reactive, it's very ready to go. So when you have carbon and when you have hydrogen and free oxygen in the atmosphere, you have boom component. That's the reality of it. That is why hydrocarbon is the core backbone of our every energy sector, so to say. Now, how do you arrange these things? Basically, think of carbon as a big heavy molecule, hydrogen is a light one. So generally you will have one carbon that is like, holding on to, let's say, 4 hydrogen. We will say that methane, CH4, one carbon is holding on to 4 hydrogen is methane. Now, when you are talking about diesel, it's generally a bit more heavier, it's more oomfish. So how the heck it gets getting more oomph? On a chemical level, it generally has C12. Basically, it has 12 molecules of carbon and it has 12 molecules of hydrogen. And the way it's arranged, sometimes it's circular, sometimes it's hexagonal things. It has a weird way of arranging itself. So generally that's how you get the more oomph out of it. So that is the reality of it. Because our atmosphere has the free oxygen to burn, and carbon and hydrogen, both of them burn very amazingly well. That is why we can use hydrocarbon, and that is why when people talk about using ammonia as a fuel source, problem is that nitrogen in ammonia, that is not gonna give energy to your combustion, it's gonna remove it. When you are talking about carbon, hydrocarbon, carbon is also gonna give energy while hydrogen is also doing the same. So that is why you get double punch. That is why every backbone of our modern industry where high power is needed, you have to use hydrocarbon. Now, the core concept is the trickiest one to understand. Is like, why the hell you have gasoline for your car, diesel for your engine, kerosene for jet fighter and all that jazz? Why the heck these things, even though they are all quote unquote hydrocarbon? Now, you have to understand few simple concepts of physics, thermodynamics, or whatever you want to call it. Think of it this way: you have a source of heat, you have heat here, whatever that way, let's say call it 1000 degrees Celsius hot element, you have that. Now if water vapor leaves it, let's say you had the chemical reaction, it was exothermic, it gave off the energy, you got that 1000 degrees. What is happening when it's leaving it? Now the leaving aspect is the velocity, basically how quickly it's going away from that. Now the lighter the component or basically compounds or elements you have, the faster it's gonna go. Simple, lighter, faster. Now but because it's light, it has much weaker basically push to it. It's not gonna push you hard. Now if you are exhausting basically water vapor, you're gonna go very fast, but you're not gonna go very you will not have a lot of oomph or newtons, so to say. But if you are pushing basically carbon dioxide, CO2, because it's a heavier molecule, it's gonna push you harder, like action equals reaction. So your because carbon dioxide mass is higher, it's gonna push you much more energetically, so it has much more newtons. However, it does not have the same velocity. Now question becomes, why the heck velocity matters? One simple reason: if your exhaust velocity, basically you have a jet engine, it's throwing magic gas out of it, that magic gas, if it's not going fast enough, you're not going to go fast enough. So it cannot be like, okay, my exhaust is only Mach 1, I'm going to go Mach 2. That's not happening. Your exhaust must be higher than that. Your exhaust could be as high as, let's say, Mach 3 or Mach 4 if you're traveling at ludicrous speed. So that's the reality of it. That's why you always have to balance these things out. If you need just a lot of heat, heavy carbon fuels are super awesome for you, because you don't need anything other than that. So we use coals in our coal power plant for that reason, because it's giving you all low amounts of heat. Now if you are you need basically a lot of thrust, you need a lot of newtons, you want to use lighter fuel. Or generally let's say in case of space shuttle, you just like, you remove carbon from it, I just want the maximum speed, so just use hydrogen. Or in case of let's say Raptor engines that are coming in the future, you can simply say, hey, I'm just going to use methane. That's like, I'm going to get a little more of oomph because carbon is there, and I'm going to get a lot of speed because hydrogen is there, more of hydrogen is there. So that's the reality of it. Hydrogen and carbon, they both burn, they both give out basically molecules. They're both stable, carbon dioxide and water vapor. So it's not like they are creating corrosive stuff or something like that. They're both stable. However, the exit velocity from combustion event is much more different, and that inherently limits your use case. So if you're like, hey, I just can simply burn it, boil water and move, no problem, use coal for that. If you're like, dude, I need a rocket engine, use hydrogen or methane or kerosene. So that's the reality of it. Now another aspect happens is that once you start simple, like CH4, if I say draw CH4, you can easily draw it. It's like CH, that's it. Now the moment you start to go into complex territory, basically C2H6, C3H8, C4H10, or like as complex as like C9H20, the ways these puppy can arrange themselves becomes much more complicated. So this is like simple example. All of these is exactly the same thing. Basically they are C4H10. So you can see how the heck they are arranged. Each of them have their different unique arrangements. Now these arrangements is the reason why the more complicated your fuel gets, basically more carbon rich it gets, it starts to create soot, because some of these puppies will misbehave and they will get basically clog up your injector plates. It will destroy turbines, which is a big issue for basically Merlin engine in SpaceX Falcon 9 system, because the turbine gets destroyed because of the sooty outputs from using kerosene. So if you're using methane, you don't have this many complexities. Now if you're using diesels have like at least I think 1300 configurations it can exist in. Why I'm talking pure raw on a chemical level, and I'm not even talking about impurities that you have to spend billions of dollars removing impurities. Just on the raw chemistry itself, it has multiple configurations. That is the reality of it. That is why it's not as clean cut as you would think. CH4 super clean. The moment you start to go into heavier carbon, you will end up with a sooty output. Now if hydrogen is the best and we want hydrogen, why the heck we don't use hydrogen all the time? Simple reality: carbon makes it more stable. So hydrogen wants to go away. It's like, you want to go away. And if you are talking about energy density in terms of kilogram, in terms of weight, basically carbon makes it much more appealing. So think of this, the more carbon you add, the stable it becomes. So basically it's not gonna fly away, it's not gonna evaporate away, and more dense it becomes. Now density is the crucial aspect, because if I give you 1 kilogram of hydrogen versus 1 kilogram of gasoline, hydrogen would be 3 times more powerful. So you're like, why don't we use it? Because it has zero density. So if I give you basically 1 liter of basically petrol, it's little bit less than 1 kilogram. It's not almost 1 kilogram, but it's little bit less. What about hydrogen? It's almost zero. It's so low that if you put it, the atmospheric pressure will push it up. So again, that's how hydrogen flies. So you can understand the density is zero. Now what if you liquefy it, how we do in rocket engines? Is still very low density. You are talking around 11 liters of liquid hydrogen to make up almost 1 kilogram. 11 liters. So you can understand this aspect, like you need a lot of hydrogen because of the density aspect, and that is why we use hydrocarbon in everything, because carbon makes hydrogen into dense puppy. So the more hydrogen you get, the more velocity you get, the cleaner outputs you get, less sooty output you get. However, you do not have the oomph, the necessary temperatures, and basically density. Basically it becomes a hell of an issue. Basically your normal fuel tank on your car will become 300 times larger. So that's the reality of it. That's why we balance these things out. You just need heat, you're like, just burn the coal. You need a bit of both. Basically you need heat, and you're like, hey, burn kerosene. You're like, hey, I want, like, very spiffy fuel, basically gasoline. Use very low carbon content and higher hydrogen content. Now, whenever we are talking about fuels, you have to understand that these fuels, even though they are quote unquote stable, even though they are like something that you can put in a pan and it will not magically evaporate, they are not 100% inactive. They react. Now, most of the time, they are very good reactants, because if you are familiar with car engineering, you know the fact that gasoline itself is used as a cooling agent in multiple places, like your fuel pump, and it is used as a lubrication in many of the bearings, and basically cleaning agent also by cleaning the intake valves. So these things are happening now because of the reactive nature, because of the high temperatures involved. There are many side effects also, so we generally add things to it, and you will never get, like, let's say you go to a gasoline petrol pump and things of that nature. You're like, hey, just pump up the gas. Are you getting pure, like, C10 H10? No, you're not. You're getting a lot of additives added onto it. Now again, it depends country to country. Some countries will have this, some countries will have that. Depending on your regulations and rules and all that jazz, you will always have something added to it. Now these additives are generally added for one simple reason. These agents, they help solve certain problems. Now let's say in case of jet fuel, when you are talking about, you have to understand that the kerosene, basically it absorbs water like there is no tomorrow. It absorbs water. Now what does that mean? That simply means if any place, when you're basically carrying the fuel and putting it into a basically fuel tank, if it's exposed to moisture, it's going to absorb the moisture. Now that's not an issue on the ground, but the moment your plane goes high altitude, as in, like, 10,000 feet, 30,000 feet or something like that, it will go into lower temperature. Side effect, you're gonna have ice formation. Now again, if ice forms on your fuel tank, it's an issue. It's not going to destroy you. But what happens if ice forms into the fuel injector? You're dead. So we have a lot of anti-icing agent, because no matter how well you control it, bad things happen, and it's better to be prepared for bad things rather than, like, hope that bad things does not happen. Then you also have to come to another aspect, that hydrocarbons are kind of corrosive in many ways. So generally anti-corrosives are also added. Now these are generally added to help with basically petrol's ability to maintain the engine, be it jet engine, be it your car engine. So these are always added to it. You will never get, oh, just give me methane, or just give me propane, or heck, you are familiar with cooking gas. You know the fact cooking gas smells, but yes, the hydrocarbon on that specific property, propane and butane, they do not smell. So how the heck you're smelling it? Because they add a agent that stinks. The reason for that is a safety system. So if you have gas leak in your home, you can instantly smell it. It's like, bro, something is wrong, so that is why there is a whole industry of additives. Now how exactly these additives work, that's beyond my ability. That's like high level hydrocarbon, high temperature chemistry engineering, that is beyond me. So I have provided the video down below where you get some context of it, and I would urge you to watch that, and also watch some dude burning jet fuel in his flame trail. It's quite amazing to watch. So I have provided the video down below. Now we come to the final aspect, cost. Now cost plays a very crucial role because if you're familiar with SpaceX, they are claiming that their new engines that are running on methane would be cheaper than the engine that are running on kerosene, aka jet rocket propellant ones. So why the heck that is? Because whenever you are talking about cost, you are talking about three things. You are talking about politics, obviously, country, the ammunition consumption, the regulation hurdles, and all that jazz. You're always talking about that. First is politics. Then we come to the manufacturing aspect. Again, if you are making something that is super easy to make, maintain, and transport, people are like, yeah, it's cheap. Again, that will directly affect the profit margin, because let's say whatever you think about oil companies, they still have people employed there. They still have dudes who have to get paid. So again, if they are not getting paid, how the heck you're gonna have the infrastructure? So these three things control the main bulk of price. So you have politics, you have manufacturing, and you have profit. After that, because these things are used in our day-to-day life, they have a lot of transportation need. Now, depending on your country's geometry, geography, and all that jazz, you can have a country that's like India. It's like, bro, we're just gonna ship gas in gas tanks, which we call cylinders here. Now, in case of Britain, you're like, yeah, it would be much easier for us to ship the gas using pipelines. So that's how you see it. Like transportation becomes another factor to it. Like if your transportation, affords bulk consumption, you're gonna be cheaper, like you're gonna get cheaper prices at higher consumption, but it will be expensive for lower consumption. While cylinders are good for lower consumption, but it becomes expensive for higher consumption. So again, you have, like, if you're running a restaurant, you would like to be connected to a gas pipe. If you're running a household, a gas tank is better option. Then we come to regulation. Now this is a critical puppy, and that is why politics is just not there. Okay, politics bad and all that jazz. No, they are there for that also reason, because regulations, think of this way, jet fuel goes into something very important. It's called a plane. Now why plane is important? Because there are 200 people relying on that minimum, and you can have even more than that. And if it falls out of sky in the wrong place at the wrong time, it could be devastating. For that reason, you have to make sure the fuel does not become the reason why your plane goes YOLO. So regulation becomes a much bigger hurdle. You have to make sure how the fuel is manufactured. Is the fuel meeting up the quality? That JP1 is a standard. Is it meeting that standard? Is the water content in the fuel low enough that is, like, safe enough? Because anti-icing agent is not like, oh, dunk 100 liter of water in the fuel tank, it's not going to do anything. It's like, 1 or 2% of water, it can handle that. So you also have to double check that. Then you also have to worry about, like, emission standards. Hey, if the fuel itself is dirty, basically we used to use lead in fuel as an additive. If fuel is dirty, you can't do anything, right? And you can't blame car manufacturers after that. So somebody has to take care of that. That is regulation. The money, large amount of money goes into that, and they have basically university is funded, and they're like, the whole sector is there where they're like, okay, this is how we're gonna manufacture fuel, this is how we're gonna handle the cost. All that jazz happens. And generally, rule of thumb is very simple. Higher the purity you demand, basically, after crude oil is refined in different things, it's not pure. It's not like, oh, you get kerosene, it's like absolute kerosene. There is a lot of mixture to it. And when you're talking about, like, LNG, liquefied natural gas, or CNG, compressed natural gas, it's not like it's just methane. There is ethane into it. So, and also for safety reasons, you have to add agents to it. So all those things generally basically make the things much more complicated, much more complicated. And so higher the purity, the more you have to pay. So you will be like, for a dumb example, you will like, think of it this way: kerosene that you can buy in a shop, a simple thing, would be $10. The same volume, let's say $10 1 liter. Now you go to jet propellant one, it could be as high as $50 per liter. Now what about rocket propellant one? That would be $500. Now again, this is just a simplified view, but that happens. The higher the purity you demand, the more expensive it becomes. So this was my presentation on the fuel aspect of the jet engine and rocket engines. I hope you liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I'd urge you to press dislike, press it twice to show me your extra disappointment. And please leave a comment, because I try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.